This video series is going to consist of the mechanical engineering basics that is often needed in mechatronic systems. Now, the mechanical engineering basics that we're looking at is the very basics of mechanical engineering principles that are often used. We're not going to be looking over here in terms of kinematics, in terms of dynamics, and other high-level mechanical calculations and techniques that are often used in mechatronic systems. But this will specifically look at material properties and how to go about with the selection of the materials, and when it comes to some of the design aspects specifically. So the first thing we're going to be looking at is the elasticity, stress and strain. Now, this is something that is, again, like I mentioned, the very basics of the mechanical engineering systems that needs to be taken into account. And so essentially what we're looking at is a piece of material. Over there it's a square cross-sectional area, and there are forces acting on it. Forces acting on it on either side, and it can be either pulling away from each other or pushing towards each other. And very similar idea and concept can be considered with this piece of plastic that I've got. So I've rolled it up into a cylinder, and essentially it's going to be tensile stress when I start pulling onto it on either side. Obviously it will go longer and it will break. You'll see there's a necking that's forming over there, and eventually it will get to the point where it stretches, and then it should snap eventually. So that is known as the tensile stress. We've got a pulling force on either side. Compression stress is now in a very similar fashion as this, where you would essentially be applying forces on either side of it. So you're pressing it together, and as you press it, the compression will cause it to obviously go somewhere. I mean, you can't create or destroy matter, so obviously it will cause it to get a little bit fatter, and that would be your compression stresses. So with this, direct stress is equal to force over the cross-sectional area. This is a very important equation to keep in mind, one that is often used, and it is used throughout this the series of videos. So this is like one of your, if you had to compare it in terms of electronics, Ohm's law, which is used for almost every single electronic concept out there. This equation is what gets used in mechanical engineering. So direct stress or stress is equal to force over area, and the units are in megapascals. Usually it's large values. You can have it also in pascals and obviously kilopascals and stuff, but generally these values are quite large. So the direct strain is the change in length per unit length in a direction parallel to the applied force. So in other words, direct strain is equal to the change in the length over the original length, or we have it direct strain as a epsilon figure. So that's delta L, which is the change of length, over L, which is the original length. Okay, so this tensiles are done usually with some tests, and so essentially you would take a piece of material, act a tensile load on it, so you start pulling it apart, and what will generally happen, as you saw with the plastic, it will start getting longer and longer. And then eventually, and as it gets longer and longer, that would be your elastic range. In other words, you can pull on it, but it will still come back to the original position. So if you had to take, for example, this, as you pull on it and let it go, it goes back to the original position. It's a bit flexible. So that's your elastic range. And then you get your plastic range, where there's deformation that happens. So after you've got this elastic range, sometimes there is a little bit of a crackling sound that might happen in the material, and then it goes, where it goes past this elastic range and gets into the plastic range. So your general extension is shown up to your point E, your maximum load point, and then after that you're going to have your local extension happening. Okay, so this is known as your stress-strain graph. The proportion between the stress and the strain, in other words, the proportional section, this straight line section over there, allows for a constant ratio. Okay, so you're able to get your modulus of elasticity, or Young's modulus is also known, which is your stress over your strain. So that is that linear part over there. And so what we're going to do is, before we continue and looking at the different equations and properties, let's do an experiment to see how these values are generated, and then we're able to see what graph we're able to get from that. To demonstrate to you how a tensor stress measuring machine is operating and how it works, I constructed this setup over here that will replicate not as accurate and not exactly the way that this machine would operate, but to give you an idea of how it works, so that in terms of the actual machine. The machine is quite large, probably as tall as a person. It's able to obviously stretch materials such as metals, aluminium, composite materials. It's quite an advanced machinery, and then it's connected to some computer system which has also got some advanced software in it that can be give you certain results. So the thing is with this specific setup that I've got over here, you will be able to sort of see the type of steps that are often followed. Obviously, with this machine, it's done in automated system. Manual measuring is not necessarily taken, or manual measurements aren't necessarily taken. So this is a more tedious process that we are going to be looking at, but it is something that will give you an idea of how things operate. So firstly, what I'm going to show you over here is the samples that usually gets used for these type of machines are in this very similar fashion, and you'll see that there's a sort of a thin necking section over here, and that necking is done so that when you stretch this material away from each other, you will actually find that this would be the weaker spot, and it would actually break in this specific area. It won't break over here on the sides or stretch on the sides, but rather on a weaker section. The machine has got certain specifications in terms of the thickness that the material needs to be able to clamp it properly. There's certain specifications in terms of the actual size of this sample that has to be. This is a very small version of the sample, and it is just to be able to demonstrate how it operates and works. What the material that I'm using is a piece of plastic material, as you would use for shopping bags type of thing. Again, much weaker compared to what these tensile measuring, stress measuring machines would actually use. But again, you're able to sort of see the elasticity and the breaking and the necking of this specific material. Okay, so essentially this shape was cut out. I then went and after I cut it out, I then just wrapped it around these two pieces over here. The one piece over here is going to be connected to my weight measuring device over here, which is measuring in grams, and that will give us that type of reading, while I'm going to be able to measure over here the specific distance that we are stretching it and correlate it with the reading over there in grams. Okay, so the first thing we're going to be doing is we're just going to be looking at what the distance of this thin necking piece is. And so I've got this ruler over here, and making sure that the measurements of where it starts off is at 0 and going all the way down, and it estimates to be 24 millimeters in length. Might not be able to see it exactly over there, but it's 24 millimeters in length. So I'm going to write over here, original length is equal to 24 millimeters. Okay, now I'm going to just set up everything so that we can then measure this. This point will be then placed on 0 over there, and we'll be able to then use this to measure how many millimeters it has moved across for every, and then we're able to measure also the amount of force acting on it. Okay, so I've generated this table over here, which you're not able to see the whole table in the screen at the moment, but as I'm going to be taking these readings, I'll record it and then I'll show you the table afterwards. Okay, so we've got this pointer positioned at position 0 over there, and we're going to then put on our scale, and so that's that's calibrated and set in grams. So what I'm going to do is I'm going to move it across to 10 millimeters, even more, bring it down to 15, 20. Okay, so I've moved it to 20, and you'll see now that it's actually caused the necking to happen. So you'll see that over there we've got the 0 position is already a bit different. It's actually set at around about 6 millimeters. So it shows that this has stretched. It's got longer. Okay, so as we're going to be pulling on this, okay, we get to 15 millimeters. That's 160 grams that we're measuring. At 15 millimeters. Okay, now I'm going to even move this further, move it up to the 20 millimeter mark over there, and I measure 270 grams. Okay, now I'm going to move it even further up to 25 millimeters, and do it a bit quicker, and I get 400 grams. Okay. Now you'll see over here that already this has stretched quite a substantial amount, because now the 0 position is actually at around about 10 millimeters. So that indicates to us it's not anymore at 0 millimeters as it was originally over there. This material has stretched a bit, and obviously this necking has become much thinner. Okay, let's move it again and see. Let's move it up to 30. Getting a reading of 340. Do it again. Okay, so over there I got actually 390 for 30 millimeters. We're going to do it again and take it to 35. Okay, 300 grams for 35 millimeters. Now notice that the readings are actually starting to decrease, and you actually see over there where it's starting to break the material. The plastic has got a little narrower neck over there, so it's probably going to start breaking very soon. Okay, let's see what value we're able to take it to now. Getting to 35. Okay, so I'm just checking to, you'll see the necking over here decreasing. So let's just go back again. Okay, let's go to 40. Go into 40 and it breaks. Okay, so at 40 millimeters it breaks. And you'll probably find that the reading was very close to that 300, and we're not going to worry about that. Okay, so as you saw that it did thin over there, it did cause a thinner neck, and then it broke over there. Right, now just to sort of see the results that we obtained over there, that would be possible to be seen, or that are tabulated over there. So that was the original length that we had was 24 millimeters, and then for the change in length, remember that was 24 millimeters plus its change in length was the actual length that we stretched it out to be, and that was a different weight measurements that I recorded as I was stretching it further and further away. I've recorded this data in this table over here. So as you can see over here, we've got our original length, which is in millimeters, and then the change in length I've actually noted over here with the weight that was measured by the scale indicated over here. Now this table I had to put into a strain and stress relationship. So remember that strain is equal to the change in length, or the delta length to be obtained over here, divided by the original length over there. So 15 divided by 24 gives you 0.625. 20 millimeters divided by 24 millimeters is equal to 0.833, etc. Okay, so when you come to the stress calculation, there are a few more things happening. I'm going to click over there and you'll be able to see the formula over here. So obviously this is in grams, and for us to get into newtons, we have to multiply it by 9.81, which I did over there. The other thing is that this weight is in grams. So force is equal to mass times acceleration. That is with the mass being in kilograms, not in grams. So therefore I've got to divide it by this 10 to the power of negative 3. Okay, to just compensate for that. And then obviously what I did, the VSS is equal to force over area. So I've got my force calculated over there, which is weight multiplied by 9.81. And the area is equal to what I've calculated over here. And essentially that is the width of the piece of material, which was 7 millimeters. And then I took into account that there was some the thickness of the bag over here. Okay, so you see the 7 millimeters over there I've taken into account for the width of the thin strip of where it was necking out to be. So that thin neck area was 7 millimeters thick, and then the bag thickness was roughly equal to well, it was between 26 and 32 micrometers when I did a bit of research and to identify what the estimated thickness of these specific bags were. So I'm averaging it to about 28 micrometers and using that in my equation over here. So I'm able to get the original area calculated over there. Okay, so it's the force, which was the weight, multiplied by 9.81 to get that force value. And then we divided that by the cross-sectional area of the bag where it was making. Remember, it's original cross-sectional area. Okay, so once I've tabulated all this, then I'm able to plot a stress-strain graph. Okay, now if you look at the stress-strain graph, if you look at the strain, it starts from 0.625, and that is roughly about over here where this yellow line is. So this graph over here would have been plotted. The issue is that this section over here, we cannot consider that to be the linear section of your normal stress-strain graphs. And the reason being is that as we were pulling out that initially that sample, and that plastic bag was stretching a little bit, when I brought it back, or when I released it, it didn't go back to zero. It actually was a little bit further. So that meant that the elasticity part had already passed by. So therefore, the plastic has got a very small elasticity section. So you probably find that if you had to use the equipment properly, or had proper equipment to do this experiment, that you would have a linear part between these two orange lines over here. It would have probably come out over there and then eventually increase over there as well, and then get to the values that we recorded. So this section over here, even though it's linear, it's not our elasticity section that we will be looking at in the sections to follow, but it'll probably be that small section over there. Okay, then just some other points to take note over here. So that is our maximum load that we were able to get, or the maximum stress that we were able to get. So that will be important for some of the calculations that we're going to be performing as well. And then this section over here was the last section we were able to look at. So if you were able to record the data just before it snapped, it would be roughly around here, and that would be where your break point is, where the fracture actually occurred. So usually these type of graphs that go up linearly, where the elasticity section is, then might even out a little bit, and then it will keep on going up again. It will get to the ultimate point. It will then start decreasing the stresses because it's starting to neck out and it's starting to get thinner in the neck, so less forces are needed to be less forces are needed to pull it because it's getting up lower and lower cross-sectional area, and then eventually it will get to a point where it actually then breaks completely. Okay, so before we actually go and look at some calculations in an example, let's just look at some formulas that are common used for these type of graphs that will be often used. So first is the ultimate tensile strength, or SUT, and this is essentially that point E on the graph. So if you remember this graph we generated, that's the maximum load point we got over there. So that would be your ultimate tensile strength, or SUT. And you would have also seen this on that graph that we did with the experiment. There was a maximum point that we obtained. So the ultimate tensile strength is equal to the maximum load, in other words, what's the maximum force that we got, divided by the original cross-sectional area. It's usually the original cross-sectional area that gets used in most of the equations, or the original length even. Okay, so that is the ultimate tensile strength. Then we got the fracture breaking stress. Okay, so there's two equations over here that we need to take into account. The one is the nominal fracture stress, which is your load at fracture, divided by the original cross-sectional length. So if you remember with our graph that we had, an experiment that we performed, you had some or other axis like this. It went up, got to the ultimate tensile point, then came down, and then eventually it broke over there. Okay, so essentially this is the point that we are looking at. Okay, so like I said, the nominal fracture stress is the load at fracture divided by the original cross-sectional area. And so we are able to identify what the load was at the fracture, or just before fracture occurred. And with that we would also have been able to identify what the cross-sectional areas if we had to measure it. Obviously it makes it very difficult when you get to a very critical point where you just can't go past it and you could actually snap it before actually measuring the cross-sectional area. And that is where this true fracture stress comes in. So you take the load of the fracture, you divide it by the final cross-sectional area at fracture. Finding that final cross-sectional area at fracture would be difficult if you pass that critical point. Okay, so nominal fracture stresses can be calculated more easily because you're able to find the load just before it fractures, and then you would also know what the original cross-sectional area was. The next section we're going to be looking at is the percentage reduction in area. So this could be quite a straightforward sort of formula, and essentially it is you're taking the original diameter, you square that, you subtract the final diameter and you square that, and you divide it by the original diameter and you square that, and then you multiply everything by 100 to get a percentage value. Remember that area is equal to pi d squared over 4. So this is another equation you will see we come across. I know that there is a way of calculating area with pi r squared, and yes, it might be a little bit less numbers you've got to enter into a calculator to be able to calculate it. The reason why I always keep to pi d squared over 4 is that most of your readings or measurements are the diameters and not the radius. And so having to convert it first into radius is one step of calculation where you could perform a calculation error. So it's always just easier to keep it to pi d squared over 4. Okay, so because we use an area over here, because it's actually original area minus final area divided by the original area, because we've got pi over 4 for each of those terms, they will cancel out with each other. And you're just essentially left with the diameters that you've got to do in a calculation. If you do the calculation using the original area, final area terms, that will be fine, you'll still get the same answer. Okay, percentage elongation. So elongation is how much longer has it become, and so the percentage in a change in length, that's equal to the total change in length divided by the original length times 100. So in other words, your final length minus the original length divided by the original length, and then you multiply that by 100. Okay, and then we've got another aspect that often gets looked at, which is a safety factor. It's always important to have a safety factor. If you know the maximum load of a piece of material is, let's say, 40 kilonewtons, would you want to design something that's able to take up to 40 kilonewtons only? You might want to make your design so that it can accommodate and that there's a safety factor of, let's say, 2, and therefore it must be able to go up to, let's say, 80 kilonewtons. So if you want to see if you want a safety factor, S would be your ultimate tensile strength value over here, and then N would be your safety factor that you take into account. So if you want to see, let's say you constructed something, got a piece of material, and you've seen that the ultimate tensile strength value is, let's say, 40 kilonewtons, and you want a safety factor of 2, you say 40 divided by 2, and that will give you then the maximum stress that you can then work with, which would be then obviously 20 kilonewtons divided by the original cross-sectional area, taking that into account as well. Okay, so let's have a look at an example. So you're given a tensile test to be performed, and it's performed on a cold worked carbon steel piece of material. You're told that the original diameter is 12.725 millimeters. After the test was done, the final diameter is 8.433 millimeters. Your original gauge length was 50.8 millimeters, so that was the original length of the piece of material. After you did the tensile test, you see the final gauge length was 60.71 millimeters. And so you're given this information. If you have the original diameter of 12.7255 millimeters, that means your original area is going to be pi d squared over 4, which works out to be 0.27 times 10 to the minus 3 square millimeters, or at least square meters. Okay, so what we want to do is we want to use this information, and that's the information that we are given, and therefore we're going to have to now do our calculations. So as you do this, you get the results, and essentially if you look at this, it is two sets of results given over here, and I'm going to draw a line over here just to separate the two from each other. Okay, so the first section is, or it continues then on to the second section over here. So we've got load over there, and then we've got the extension in millimeters over there. So those are essentially what is being recorded, and that's what you are given. Okay, so for every set of load that we did, as we did in the table with the example of the piece of plastic that we were stretching, we were getting these different loads, and there was a correlating extension in millimeters or change in length in millimeters. So this information is supplied to you over there. And then it continues with, as the load goes to 64.7, it's an extension of 0.152, and it keeps on going up to 72.8 kilonewtons. Alright, so now after you've done that, as we did in the table on a spreadsheet where we converted the load and the extension, we had to convert it into stress and strain. Okay, so keep in mind that stress is equal to force over area. So you take this force, so you take 5.5 for example, and you divide by the cross-sectional area, the original cross-sectional area, which is 0.127 times 10 to the minus 3, and you would then get the stress value of 43.25 megapascal. Okay, so that is how these stress values are calculated. Again, load of 11.7 divided by 0.27 times 10 to the minus 3, and that gives us our 92 megapascals. So you're able to calculate that for all the values coming across over here and continues over here as well. Okay, remember that strain is equal to the change in length divided by the original length. Okay, so we are told that the original length was 50.8 millimeters over there. So therefore we can say that the extension over here of 0.010 millimeters divided by the original length of 50.8 millimeters is equal to 0.197. Again, if we look at over here where we have an extension of 0.02, we divide that by 50.8 millimeters and we get a value of 0.393. Again, if we come down over here, we would see this extension of 0.152 millimeters. We divide that by the 50.8 and we will get a value of 2.99. Keep in mind that all these strain values are multiplied by 10 to the minus 3. And so, therefore, if you look at this 0.152 divided by 50, you don't think, oh, it's going to be equal to 2.99, but it's 2.99 times 10 to the minus 3. It's an important fact just to keep in mind that that's always in your strain values. Okay, so we're able to generate this, these points, and from this we're actually able to identify that the maximum load is 74.3 kilonewtons. At least that is something that would be given to you as the test was performed. Okay, so now you've got to plot this stress strain graph. Okay, and obviously if you're given some graph paper, you can do a proper job with it and actually do the plotting of the points. If you don't have graph paper with you, then it will have to work on a very sort of rough estimation of what it would look like. Obviously you can take these stress and strain values and you can actually put them into a spreadsheet and then let that spreadsheet plot the graph for you. Okay, so if we have to look at this, we're going to draw the stress strain graph. So we've got our axes, which is on our y-axis as such. Okay, so that is stress, and that's in megapascal. And then we've got our strain. Okay, and remember that is times 10 to the minus 3. Okay, so now that we've done that, you would start plotting these points for the stress and strain, and we'll be going up at a linear fashion. And then for this specific example, it will curve out, and then once it's curved out, it will keep on going up again, and eventually it will get to the maximum point or maximum load that you're able to get. Okay, so we're going to be using this, we'll be coming back to it very soon as well, just to do some calculations, but things just to keep in mind again: stress is equal to force over area. That's our one important equation that we have been using over here, as well as our strain is equal to the change in length over the original length. Okay, so now we're going to be looking at different things that you could be asked to calculate. So the first thing we'll be looking at is the limit of proportionality. Okay, so that is where we say E is equal to the stress over the strain. Remember, this is also known as our modulus of elasticity. But essentially what we're going to be doing is we'll be looking at the linear section of this graph that we just plotted. Okay, so if we have a look at this linear section, you will see that essentially, so we're looking at this linear section over here, and we're going to be looking at taking any point over there, which we'll take for example over there, and you'll realize that would be around about 417 megapascal. Okay, so essentially we can say our limit of proportionality, that's where this linear section then goes and ends, roughly is at the 417 megapascal. Okay, so keep in mind it's on the linear section. Okay, and that's where the straight line ends, and that is roughly equal to 417 megapascal. Right, the next thing we're going to be looking at is the modulus of elasticity. Okay, and so that's again on that linear section of that graph that we're going to be looking at. So modulus of elasticity is equal to the stress over the strain. Okay, and essentially what we're going to be doing is we're going to be looking at any of these points over here on this linear section. Okay, and if you look at the points on this linear section, we can actually identify the 2 points shown over here in the data that we obtained of 133.67 megapascal, and the strain correlating that is 0.59. Okay, so we're going to use those two specific values. Okay, so that is equal to 133.67 times 10 to the 6, because it's megapascal. Keep in mind you always have your units that you need to have over there and have the correct exponential values for the multiplication of 10, and we divide that by 0.590 times 10 to the minus 3, and that's equal to 226.55 gigapascal. Okay, so keep in mind there's any point of the linear section that we're going to be looking at. Now, the next thing we're going to be looking at that you probably need to find out is the ultimate tensile strength. So the ultimate tensile strength as such. Okay, so remember UTS is equal to the max load, divide that by the original cross-sectional area. Okay, so max load, if you recall correctly, we had been told over here that's 74.3 kilonewtons, so we're going to be making use of that, so that's 74.3 times 10 to the 3, and we're going to divide that by the cross-sectional area. Now remember, we did a calculation, the original area is 0.27 times 10 to the minus 3 square meters. Okay, so that is 0.127 times 10 to the minus 3. Do that calculation and we get an answer of 585 megapascal. Okay. So that 585 megapascal, if you that is something we will also be looking at a bit later, but again that is there where this maximum stress over there has been obtained. So if we had to, that's using that force over there. Okay, the next thing we've got to do is, let's say you've got, you're told that you've got a 0.2% proof strength. Okay, so let's just do a quick calculation. 0.2% is equal to 2 times 10 to the minus 3. Okay, so essentially what we're going to do is, if you look at your strain values over here at the bottom, you'll find it will be where 1 is, and you'll find where 2 is. 2 would be over there roughly. Okay, and so what we're going to do is we're going to draw a straight line with this parallel line that we've got over there. So you'll use a ruler and you'll draw a straight line over there. Okay, as a matter of fact, if you have a look at this, you'll probably find that 2 would be over here and 1 would be over there. That's a more accurate type of reading. Okay, so ignore this line over there. So we'll draw the parallel line over there, and we'll look at where it intersects, and it will intersect roughly over there. Okay, so we take that point where it intersects the graph and we draw it across on the y axis. So if we project that across, we'll find it to be roughly about 555 megapascal, that specific point. Okay, so therefore for this we will say that for a strain of 2 times 10 to the minus 3, we're going to be getting a stress of 555 megapascal. Okay, so that's how you would do your 0.2% proof strength. Now the next thing that you could be asked or have to calculate is a percentage elongation. Percentage elongation. Okay, so remember that the percentage of the delta L is equal to the final length minus the original length over the original length. That's an F over there. Okay, so that is equal to our final length. We are told that that is, if you remember in the question we had to look at, our final length was 60.71 millimeters. So that's 60.71 millimeters. Our original length, we are told, is equal to 50.8 millimeters. Okay, so minus 50.8 millimeters. Again, all of this is times by 10 to the minus 3 because it's in millimeters. And then we divide that by 50.8 times 10 to the minus 3 meters. And we've got to multiply it by 100. Remember that's that over there times 100. So we multiply it by 100 over there. Okay, and we get an answer of 19.51%. So remember this times 10 to the minus 3 over there will cancel out with each other if you wish to do so. Okay, and then finally you've got to calculate the percentage reduction in area. Okay, alright, so remember that the percentage of the change in area is equal to the diameter of it being over here we'll say original squared minus the final diameter squared divided by the original diameter squared, multiplied by 100. Okay, so remember that our original diameter, we did do a calculation of that. We indicated it was equal to well, we've got it over here. It's 12.725 millimeters. Okay, so 12.75 millimeters, or 725 millimeters, and that's all squared, minus what was the final diameter was 8.433. Okay, so minus 8.433 squared, and again divide that by the original, which is 12.725 squared. Now each of these values should be multiplied by 10 to the power of minus 3, but they do cancel out with each other. Okay, so after I've done that, I'll multiply that by 100, and then we get a final answer of 56.08%. Okay, let's have a look at shear stress and shear strain. So this is different to your tensile stress and tensile strains that we've just been looking at. So what is shear stress and shear strain? So if you had to take, for example, this piece of noodle that I've got, obviously we said tensile was if you had to pull on it on either side, but shearing is when you've got this noodle, for example, as we've got over here, and you have to almost go and hit it from the side as such, and it would snap. Well, it should have snapped into two pieces over there. Obviously my finger was quite thick over there, but if you had to take this and suddenly you had to snap it, it would be a clean cut between the two pieces, and that would be known as your shearing. Okay, so it's a different type. It's the opposite or 90-degree forces acting on a piece of material as you would have with a tensile stress. Okay, so the formula for average shear stress is equal to the shear force over the shear area. Okay, so remember again, we've got that magic formula of stress equal to force over area. In this sense, the only difference is we're looking at shear force and we're looking at the shear area. Okay, and obviously sometimes your cross-sectional area could be the same as your shear area. The equation is very much the same. The only difference is that the shear stress is given the symbol tau, shear force is given the symbol V, and the shear area is obviously still area. Okay, so the units are in pascals or newtons per square meter, and it's only valid for small cross-sectional areas, so spins and rivets, that type of scenarios that you would using. Okay, so let's just have a look at the modulus of rigidity. Okay, so the modulus of rigidity is the shear stress over the shear strain. Okay, so rigidity is given the symbol G. Shear stress is equal to tau, which we've calculated over there, and shear strain is equal to this gamma, or it could be like a Y type of symbol. Okay, so remember your modulus of elasticity. It's the same, very similar equation of stress over strain. It's just looking at the shear aspect of it. Okay, so this is your shear strain that we're looking at. And essentially how that equation came about is that if you had to take this piece of material over there and you had to shear it so that the bottom piece goes towards the right and the top piece goes towards the left. Okay, so obviously that over there is an angle that we are looking at. Okay, so if we say tan of that angle is equal to this stress value over there, or delta value over there, over BC. Okay, so that delta value over BC is equal to the tan of that angle. Alright, so as the angle is equal to the tan of that angle for small values of that angle, Now remember, these angles are in radians for this equation to be valid. We can say that that angle in radians is equal to that change over there over BC. Okay, so there's two types of ways that you can go about with these shearing of materials. So you could have a single shear, and that could be like, for example, in this scenario, you've got two pieces of materials that are lapped on top of each other, and there's a pin going in between in between it. So it's going through the two materials as such. Okay, and that pin is preventing the movement of the two materials away from each other. So obviously, as you can see over there, if you've got a spin going through these two materials, if one is acting on a force in that direction, the other one's going in a force in that direction, you will have that it will shear on that pin at that specific position. Okay, so that's known as a single shear. Then we've got a double shear. So for example, you could have a fork-like structure over here where some force is applied to it, and inside that fork you've got a single piece of material that goes in there, and it's got a hole against through it with a pin going through it as well. And so if you apply these forces and it's too much to either force, it will shear on both of those two points over there. So there's 2 points of contact where these materials are making, and therefore there will be a double shear happening. Okay, so keep in mind the double shear is about 2 times compared to a single shear. Okay, where do these shearing type of scenarios occur? Well, one of the situations where I was involved with accident specialists in Durban, South Africa, has been in terms of reconstruction of accident scenes. And so what we were involved with was the remote control of a vehicle that we could cause to impact a trailer of a truck, as seen over here, and we wanted to hit it on the side over here on the back of the wheel, because this is a common accident scenario that occurs. And so we made this vehicle, got it to remote controlled, and we were able to then hit it. And as you can see, the wheel shaft sheared completely off over there and over there because of the forces acting on it. The force of the trailer was acting against the motion of the car, and the car was coming from this direction, hitting the wheel, and it sheared the wheel off the shaft. So that's a typical scenario that you could come across where shearing of materials actually occur. Okay, so let's have a look at an example. Let's say we've got a lap joint, and it's got 4 rivets going through it, and subject to a load of 55 kilonewtons. Determine to the nearest millimeter the required rivet diameter if the allowable average shear stress is not to exceed 75 megapascal. Okay, so if you remember from our formulas that we looked at, we've got stress is equal to force over area, but again we're looking at shear stresses and shear forces. Okay, so area is equal to V over tau. Okay, so that is our formula rearranged. We looked at tau equal to V over A. We just rearranged it so the area is the subject of the formula. The thing is though, is if you look at the area, it's 4 rivets that are lap joints. So in other words, there's 4 times the area that we are working with. So therefore we've got 4 times over there that we need to take into account. Okay, and we're told that that is equal to, we know that our load, which is V, is 55 kilonewtons, so that's 55 times 10 to the 3. And we know our tau value, which is our shear stress, is equal to 75 megapascals, so that's times 10 to the 6. Okay, and that is equal to 7.33 times 10 to the minus 4 square meter. Okay, but that is 4 times the area. Okay, so we need to now look into that. We have to calculate what is the diameter of the rivet. Okay, so therefore 4 times, now the area is equal to pi times d squared over 4 is equal to 7.33 times 10 to the minus 4 square meters. Okay, so that 4 and that 4 can cancel out with each other. Okay, so essentially d squared is equal to this 7.33 times 10 to the minus 4 divided by pi. Okay, and that will be equal to 2.333 times 10 to the minus 6. Okay, now we've got to calculate d, so we take the square root of both sides, so therefore d is equal to 15.27 times 10 to the minus 3 meters. Okay, the question is asking you, determine to the nearest millimeter the required rivet diameter. Okay, now the problem is you can't go and say over there, well, I'm going to say 15 millimeters, because if you do 15 millimeters, it means that this system will fail for those stresses that we are looking at. So we can't use 15 millimeters. It's not going to be safe. So we've got to go to the next available millimeter, which is 16 millimeters. Okay, so that implies that d is equal to 16 millimeters.